Right, so today we have a very special event. We have Guillermo Arias Tamargo and Elli tell us about machine learning brainwebs. Take it away.
Okay, so thank you very much, Julius, for having us here and allowing this kind of weird format joint presentation. So what we're going to talk about is this paper from a couple of months ago that we did with Yang-Hui He, Ed Hurst, I don't know if I pronounced it right, and Diego Rodriguez Gomez. And the sort of big question that we were trying to address is the question of 5D SCFTs. I guess that in this audience, you're already quite, I don't have to convince you why this is a good question. These theories, long ago, it was thought that they couldn't exist because there are no normalizable terms that you can write in 5 dimensions. But then it turned out that, in fact, they do exist, and there are a lot of them. And so the famous paper by Cyberg, he built them with branes, and then also there were constructions in geometric engineering and so on. And lately, the perspective has been more than actually maybe it's a good middle point where there are enough constraints coming from superconformal symmetry in 5D to be able to know the full landscape, but also there is enough variety to have interesting phenomenon going on. So one of the preeminent examples of this sort of way of thinking is the attempts to classify all these 5D SCFTs from the geometry. And the idea is that you can engineer these theories from M theory on a Calabi-Yau threefold, which is not, what's the word? Compact, so that gravity is decoupled. And in this case, you can translate the classification that is known from mathematics of canonical singularities into a classification of the 5-dimensional superconformal field theories. And in this case, this classification, it grows complicated as you increase the number of moduli of the Calabi-Yau, which translates to the fact that in physics terms, it grows more complicated as you increase the rank of the 5D theory. And then, well, we know that this happened, but we also know that you can build these theories from branes. So we ask, can this classification idea be addressed from the brainweb's point of view? So one key point that hints that yes, it can, is that so all the low rank theories that were realized in this sort of systematic way from the geometry, it turned out that they all have realization as more or less complicated brainwebs. And then approaching this classification problem from this point of view, conceptually is really simple. You just start by fixing some number of external legs of your brainweb. Then you scan over the possible charge values that these external legs have. And once you have this, okay, you just, this is in principle doable, list all the brains, all the webs that can hang from these external legs, and then mod out from all the webs that give rise to the same 5D theory. And then you just go to the next step, increasing the number of external legs. Now, the point is that this, in particular, this step of modding out all the equivalent webs in practice is very difficult. So what we did is have a neural network try to do this part for us. Now, one good thing that this approach has is that it grows complicated with the number of external legs. This is quite obvious from this sort of scheme. And this is nice in that it complements the classification program from the geometry, in the sense that for this approach, increasing the rank is really not an issue. And today, what we're going to talk about are the first steps of implementing this idea in the simplest case, which is where the brainwaves have 3 external legs. So with that in mind, the talk of today, I'm going to, well, give you the introduction. I'm going to give a brief review of brainwaves, which I guess maybe it's not too needed here, but just in case. And then I'm going to say some things about some invariant quantities that, this name will make sense when I get there. They are sort of the starting point that we need for to give data to the neural network. And then Elli will take over and explain to you what neural networks are, how we use them, and what are the results that we got. Okay, are there any questions so far? Okay, so brainwaves, as probably all of you already know, they can be built in Type IIB String Theory. Here you have D5 branes and NS5 branes, and when you join them together, even if in principle you could expect from the similar picture in Type IIA that the system is something like this, it turns out that no, there needs to be some form of charge conservation, and one of the branes will be diagonal and it will carry charge under both the Ramon and the Neves-Schwarz 2 forms. And in general, you can not only have this 1-1 brane, but you can also have general PQ 5 branes. And this thing here, it serves as the building block where you can build then more complicated brainwaves and more complicated theories. Sometimes you can read a Lagrangian description from this in the low energy limit. Sometimes you cannot, such the cyber theories. And one extra ingredient that you can add is have these external legs instead of go all the way to infinity, having them end on 7 branes. And this increases the landscape of theories that you can build. But also it adds some complications, essentially due to the fact that the 7 branes, they act as a source for the axiodilaton, which looks like a complex logarithm. And then this logarithm has a branch cut, which is the monodromy cut associated to the 7 brane, that tells you that as you go through it, you have to transform all your fields by monodromy associated to the 7 brane, which depends on its charges. Now, one nice thing is that understanding the possible deformations of the theory can be visualized really easily from the brainwaves. Maybe in the directly in the field theory, it could be more complicated. So this movement where you have the brainwave and you open a face corresponds to moving from the origin to another generic point in the Coulomb branch. You can also move subbranes in the perpendicular direction from the screen, and this would be a movement on the Hitch branch. And perhaps more important for our purpose is that you can just grab a 7 brane, move it around. This will bring with it the 5 brane, which ends on this 7 brane. And this is a deformation that's not free in terms of energy. This is not part of the moduli space. This is like a physical mass deformation. And in general, if you have a web with L external legs, the number of independent such deformations that you can have is L-3, and this comes about because, well, in principle, you say, okay, I have 7 branes and I want to specify their positions in the plane of the brainweb. So you have 2 L parameters, but then you can remove a lot of these. First, because the movement of the 7 brane along the leg does not affect the longitudinal physics. So this removes the 2, you are with L. Then you can also rotate and overall move the center of mass of the brainweb, and this removes 2 more degrees of freedom in this sense. So you'll be with L-2. And furthermore, you have to impose charge conservation in all these junctions on the brainweb, and this leaves you with L-3. And this is why I mentioned at the beginning that in this first step that I'm presenting to you today, we focus on the case with 3 external legs, because then we don't have to worry about these deformations and specifying the web. We just need to specify these external legs. So in particular, we need to specify the P and Q. These are the charges of the same brane, and N is the number of 5 branes that end on this given 7 brane. And even then, even in this already easier case, we have to take care of the key point, which is there are many webs that give rise to the same theory. So one such way is the S-duality of type IIB. You take your web, you transform everything with an SL2C transformation, and the theory will stay the same. And another source of these equivalence classes of webs are the Hanani-Witten moves, which consist on you start with a given brainweb, and you grab the 7 brane and you move it along the leg, which I already told you that this doesn't change the low energy theory, and this stays true even if you move it through the junction. And this is a 2-step process. Once you move it through, you have some branes are created or annihilated, and then you have this monodromy, which you have to bring all the way back there so that it goes away from the brainweb. This is what's the source of the complications, because if I give you 2 webs, it's not an easy problem in principle to determine whether or not there exists a set of Hanani-Witten moves and S-duality transformations that bring one into the other. And this is where the neural network will be of use. But before getting into that, I need to tell you about some quantities that are invariant under all these moves, and that serve as the starting point for us. So this is work that from a long time ago, a series of papers by different subsets of this collection of authors during these years. And what they did, they studied, well, they didn't study 5 brane webs, they studied PQ string junctions, but this is a problem which is very similar to ours because it's related by 40 dualities. Yes?
Yeah, just a small question about the slide before. The configuration that you say is hard to know if they are equivalent. Is it only for 3 branes or more? Or do you say that even for 3 it's already...
Even for 3 is problematic.
Even for 3, okay. Okay, thank you.
But and when you increase the number of legs, it grows more problematic. Okay, so as I was telling you, this group, they studied PQ3 junctions, and they noticed that there are certain quantities that remain invariant under these transformations, and these quantities, they can also be defined in our case of 5-frame webs, and are extremely useful. So the first of these is the total monodromy. The total monodromy of the web. This is simply defined as if you have, in our case, 3 7 branes, each with their own monodromy. So if you go around them all, you have a total monodromy, and the trace of this is an invariant. The second invariant that we use is so-called asymptotic charge invariant, which is defined as the determinant of this matrix from the P and Q charges of the 7 branes. And if you take the greatest common divisor of all of these Lij, then this quantity is also invariant under all of these moves. And last but not least is this self-intersection I, which well, it has this particular form, and it's interesting to stop a second in this self-intersection because it has a very clear geometric interpretation, and it's useful to understand it a little bit better. So the reason is that this system of PQ strings hanging from 7 branes in Type IIB can also be understood in M theory as M2 branes that grab different 2 cycles in an elliptically fibered K3. And in this picture, the self-intersection I that I just defined is literally the self-intersection of these 2 cycles grabbed by the M2s. And from this point of view, there are certain conditions that this need to satisfy as a necessary condition to ensure supersymmetry. And in particular, this that for these cycles to be holomorphic, the self-intersection needs to be greater than -2. Which is a condition that we will need to impose when we generate our data for the brainwaves. And also, this self-intersection is then related to the genus, which then is again related to the dimension of the Coulomb branch. So from it, we can also get for free basically the rank of the 5D SCFT. So this is why I was telling you that increasing the rank is not really a problem for us, because when we do the scan over the P's and the Q's, it's just a one-step computation to obtain which is the corresponding rank. Okay, so let me recap what I've told you so far. We have the objective to classify the possible inequivalent brainwaves with 3 legs. We know that there are 3 invariant quantities, and in particular, since we know that they are invariant under these moves, this means that if we know 2 webs that have different invariants, then we are sure that they really are different. So this will be important as the starting point of the classification. We use the simplifying assumption as a first step to look only at webs with 3 external legs, in which case we just need to specify which are the 7 branes of where these external legs hang. And then the strategy will be to approach this problem of classifying which webs are equivalent and which are not by means of using a neural network. And the point is that, as I told you, it's difficult to distinguish whether 2 webs that have the same invariants are the same or not, can be moved from one to the other using Hahn-Witten moves and so on. But what is easy to do is, if you have one web, perform many Hahn-Witten moves and S-duality transformation, have a lot of data, then feed this to the computer and hopefully recognize some pattern. And this is the part that Elli, who's the real expert in the neural networks, will tell you about. And I guess that this is also a good point to stop for questions, if you have any.
Guillermo, I have one question. It's Mohammed. When you look at the external legs, do you assume that you only have black dots in the toric diagram?
No, we can have many fibrils hanging from the external leg.
Okay, fine. But I was confused because you said like the three numbers are PI, QI, and NI.
Mm-hmm.
So what's the data that tells me there are white dots in the diagram?
So if NI is different from 1, you would have a white dot, no? Because you will have several fibrils ending on the same.
Okay, I understand. Okay, thank you.
Okay.
But you didn't assume that the GCD of P and Q is 1?
Yes, this was a problem when, like, for this particular formula and only here,
Okay.
I'm using the total charges of the legs.
Okay, okay. But in the other one, you assume that the GCD is always 1.
Yes, exactly.
Yeah.
Okay.
Okay, so I guess if there's no more questions for Guillermo, I'll take over. So I should briefly introduce myself because I don't think I've met many of you before. So I'm Elli, I'm a PhD student at City in London, and I use machine learning to study objects in string theory and algebraic geometry. So today I'm going to give you like a mini crash course on some machine learning and then talk you through the results that we got in our investigation. But firstly, I want to talk to you about how we generated the data for brainwebs. So as Guillermo has already said, we just looked at 3-leg brainwebs. And for 3-leg brainwebs, you can encode everything into a set of 9 variables. So that's namely the PQ charge values of the 7 brains and the multiplicity for each of the 3 legs. And then you can encode those 9 variables into a 2x3 web matrix. And the goal that we wanted to achieve was, given 2 of these web matrices, determine using machine learning whether or not those 2 webs are equivalent or not. So do they describe the same physical theory at the junction? So you can sort of interpret this as like a binary classification problem where your output is 0 if the 2 webs are equivalent, inequivalent, and 1 if the 2 webs are equivalent. So we used 2 different definitions of equivalence in what we did. The first definition we refer to as weak equivalence. And that means that 2 webs are weakly equivalent if they share the same number of legs, which is always in our case because we're just looking at 3-leg brainwebs. They share the same rank, the same total monodromy, and the same asymptotic charge invariant. So the second definition of equivalence, which we refer to as strong equivalence, says that 2 webs are strongly equivalent if there exists a known sequence of physical preserving transformations to go from one web to the second web. So you could do an SL2Z transformation on the whole web, or you could do just, a Hanani-Witten move on one of the legs. And another thing you could do is just simply relabel the legs in the brain web. So that would correspond to permuting the columns in the web matrix.
I have a question.
Please.
How do you come up with the 2 sets of brainwebs that you are generating?
So what? Choosing the charges?
There are plenty of webs in the world.
Yeah.
So
that.
How do I choose? You gave me data.
So
how do I choose this data?
So the data, basically, we generated all possible sets of the 9 variables with the charge values in this range, -3 to 3, multiplicities in the range 1 to 3, such that you have coprime charge values. The sums of the charges have to be equal 0 because of Gauss's law, and the intersection number has to be greater than or equal to -2. So it's really just like randomly generated.
Exhaustive chart. So here it's just exhaustive, you said.
Yeah, so they're randomly generating, no particular type of webs in particular.
I see. Okay, thank you.
Cool. So yeah, that's how we generated the data. And then moving on to machine learning. Most machine learning algorithms you have can either be broken down into supervised learning or unsupervised learning. I say most because there's actually other categories like reinforcement learning or semi-supervised learning, but we'll ignore those for today and just consider these two. So supervised learning is used when you have labeled input-output data and you want to find a mapping function to go from input to output. Whereas unsupervised learning, on the other hand, is used when you have unlabeled data and you want to try and find some sort of pattern or structure within the data. And unsupervised learning can be roughly broken down into dimensionality reduction or clustering algorithms. And supervised learning, on the other hand, you have two types of problems. You have classification, where your output variable is a discrete class, and you have regression, where your output is a continuous numerical value. And then we can break down classification one step further, where you have binary classification, which is just two classes, or multi-class classification, where you have more than two classes. So as I mentioned on the first slide, we were looking at the problem of given two brainwaves, determine whether or not they're equivalent or not. So that's an example of binary classification. So we mainly did, yeah, like I say, binary supervised classification, but we also did look at dimensionality reduction to visualize the data. And we'll see that in a little bit, but I probably won't have enough time to go into depth on how the algorithm works. But I do want to talk about how a neural network works, because that's the main algorithm we used. So very briefly, neural networks are made up of building blocks of neurons.
A question? So before getting into the details, can you give the final result? How many different webs did you find in the range you looked for?
So our data set was comprised of about 700 webs. And then we were just determining pairs of webs within that data set, whether they're equivalent or not.
Okay. And how many did you find? Inequivalent?
So I mean, so in machine learning terms, you want the number of equivalent webs and the number of inequivalent webs to sort of be equal size classes, so that you don't get like a biased result. Because in reality, obviously, if you randomly pick two brain webs out of a hat, they're more likely to be inequivalent than they are to be equivalent. So that's a very easy problem for machine learning to learn, because it would just always predict that they're inequivalent and you get like 90% accuracy. We actually force them to be the same number of inequivalent webs and equivalent webs.
I would consider an important question: if you give a certain range and you compute the number of inequivalent webs that you find there, not within a pair. You want to find number of different theories which are possible within a different range. So within a given range. Right? So that's an important question. Right? If you find 300 different models, then we could argue for some kind of a classification, and then find make an attempt to study them in a systematic way.
That's interesting. We didn't, well, I can't think at the moment like how many webs within the data set we used were actually equivalent or not, but I can definitely go back and find that. And that's because we have the data generated already, so that's an interesting thing to look at. Thank you.
It will be a very important point to classify if there is an additional order parameter that could arrange them in a certain order. And just talk about a list. Here's the simplest one. Here's the next one. Slightly more complicated. If there are criteria, in general, it is a difficult problem. But I
mean, yeah, that would be interesting to sort of rank their difficulty, because you could definitely look at the results of where the neural network is predicting that they are inequivalent when they are actually equivalent, and if that's happening at the same time with one particular like troublesome web, you could say that's a difficult. So yeah, but thank you for that suggestion. I'll think
Thank
about.
you.
So yeah, going back to neurons. So we have this set of input values, and you do a weighted sum with additional biases. And then you pass that weighted sum through an activation function, and you get a single numerical output. So the activation functions in neural networks are really, really important part, because without them, or if you just use linear activation functions, then your whole neural network would just be sort of like a complex linear regression model, and it wouldn't be able to pick up that complex data. So by using a nonlinear activation function, you're really able with a neural network to determine complex structures and patterns within data. So there's loads of different types of activation functions you can use. I've just given 2 examples here. First of all, rectified linear unit, or ReLU for short, which is y is 0 for negative x, or y is x for positive x. And another common example is hyperbolic tangent. But yeah, as I said, there's lots of other different types that people use in sort of different situations they work best. So that's what a neuron is. And then going on to a neural network is simply layers of neurons that are fully connected. So they're all connected to each other. So you have an input layer, which is fed your input data. You have one or more hidden layers, which do the computations that we just discussed. And then you have an output layer, which outputs your final prediction. So in a classification problem, the number of neurons that you have in your output layer corresponds to the number of classes that you have. And the value you get from those output neurons corresponds to the probability of the input belonging to that class. So say if we fed an input in here, it traveled through the network, and we got an output of 0.4 and 0.6, we would predict that the input belongs to this class, because it has the highest probability. And this process of feeding information forward through the network, we call feed-forward propagation. And when you have an output, you want to compare it to the true value. And we do that using a loss function, which I've denoted as J here. So typical loss functions for regression problems would be like mean absolute error or a mean squared error. Whereas for classification problems, we use a loss function called cross-entropy loss. And the whole goal of training a neural network is basically to update the weights and biases in the neurons such that you're minimizing the loss. And the way that we do that is by a method called gradient descent, which essentially it does what I just said. So it updates the weights and biases in the direction that you move your loss towards the minimum. And to do gradient descent, we need to know the partial derivatives of the loss function with respect to all of the parameters. And to do that, we have to go backwards through the network. So we work and we compute the partial derivatives in the layer below the output layer, and then again until we get to the input layer. And finally, what I want to say is that when you have a data set, we split it into a training data set and a test data set. And then we train our neural network on the training set, and then we make predictions on our data in the test data set and compare that to the truth so that we're getting an accurate and unbiased evaluation of the network. So just to summarize what we've just said, so we get given a data set, we split it into a training data set and a test data set. Then for each data sample in our training data set, we do feed forward propagation, pass it through the network and get a prediction. And then with all of our predictions in our training data set, we compute the total loss. And then we perform gradient descent. Well, first we do back propagation, compute all the partial derivatives. Then we do gradient descent to minimize the loss. And then we have a trained network. And with our trained network, we can then do predictions on data in our test data set and compare that to the true value and get an evaluation of our network. So that's what a general neural network does. And I want to talk about what a Siamese neural network is, because that's the particular type of architecture that we used. So Siamese neural networks are most commonly known for use in image recognition, but essentially you can use them in any situation where you're wanting to compare the similarity of two inputs. So in our case, we want to compare whether two brainwebs are equivalent or not. So similarity is equivalence in what we're talking about today. And as the name of the network kind of suggests, they're made up of two or more identical subnetworks. And the role of the subnetwork is to produce a d-dimensional embedding from your given input. And we trained our Siamese neural network using what's called a triplet loss. And so the network comprised of three subnetworks that they share exactly the same architecture and exactly the same parameters. And we trained it on data in the test data set with triplets. So you have an anchor web, a positive web, and a negative web, where the positive web is one that's equivalent to the anchor web, and a negative web is one that's inequivalent to the anchor web. So the goal was train a Siamese neural network such that the embeddings that you get of the webs that you input is such that the squared Euclidean distance in the embedding space between positive and anchor webs is smaller than the distance between the anchor and negative web embeddings. So that's what you can see in the definition of the loss function here. You have a 0 if the difference between these two distances is greater than this parameter alpha, and otherwise it's the differences between the distances plus this marginal parameter. Okay, so eventually we want to get this picture we see here. So we have the anchor negative webs, which are inequivalent webs, are mapping far away in the embedding space, and the anchor positive pair, which are equivalent webs, are mapping close together. So you're sort of like in the embedding space, you're clustering similar webs or equivalent webs, and you want the clusters of inequivalent webs to be far apart from each other. So we have an R6 dimension here, because we're doing a 2x3 web matrix, which we actually flatten before we feed it into the network. And our embedding dimension is R10. And we chose D to be 10 simply because we tried out a few different size dimensions, and 10 seemed to give us the best results, so we went with that. So yeah, to summarize the process, we had two different data sets. We had our X and our Y data set for weak equivalence and strong equivalence. And for each of those, we did the same procedure. We split the data into training set and a test data set. And then we trained the Siamese neural network on triplets from our our training data set. And then with the trained network, we then created embeddings for every web in the test data set. And then we predicted whether two webs in the test data set were equivalent or not, based on if the squared distance between their embeddings in the embedding space was below or above this threshold parameter lambda. So if the distance between the distance between the two embeddings was greater than lambda, we predicted them to be inequivalent, and if it was less than or equal to lambda, then we predicted them to be equivalent. So that's what a Siamese neural network does. That's the procedure that we did. Now we can have a look and discuss the results. So as we said, we had our weak equivalent data set X and our strong equivalent data set Y. The percentages you can see here are the accuracy of the pairwise equivalence predictions in the test data set. So this that we just discussed. And the plots you can see here is as I mentioned a few slides ago, we did some dimensionality reduction algorithm. So that's what's used here. So we embedded the webs in the test data set into 10 dimensions, but obviously we can't visualize 10 dimensions. So we used a dimensionality reduction algorithm called t-SNE to reduce that down to 2 dimensions. So briefly, t-SNE is a an algorithm that maps data in a high dimensional space to a lower dimensional space, such that the similarity between data points in the two spaces is as low as possible, where similarity between data points is defined as the conditional probability that one data point will choose the next data point as its neighbor. So each data point in the plots that you can see represents a web in the test data set embedded into 10 dimensions, reduced down to 2. And they're color-coded based on their equivalence class. So the first thing we did was look at the simplest possible thing we could think of, which is having just 2 equivalence classes. And you can see for the X data set, we're getting 100% accuracy in the test set, which, even though it's a simple case of just having 2 classes, 100% accuracy is really, I think, quite an impressive result, because if you think about how to compute weak equivalence of 2 webs by hand, you have to, determine whether they have the same number of legs, which is an easy thing to do, but you have to compute their rank, their total monodromy, and asymptotic charge, and compare those between the 2. And those 3 computations together is actually quite involved. So the fact that the neural network is getting 100% accuracy is really exciting. And in the t-SNE plot, you can see 2 very nice distinct clusters. So that's the picture that we really want to see at the end. However, in the Y data set, in our strong data, we're getting the opposite case. We're getting 50% accuracy, which is the worst possible result, because it means that the network is doing no better than just randomly guessing whether 2 webs are equivalent. And in the t-SNE plot, you can see this supports that, because it's just a jumble of the 2 different classes. We're seeing no clustering whatsoever. So moving on to the full data set of the 14 classes, in the X data, we're seeing a drop from 100% down to 77%. But again, talking about how difficult it is to determine weak equivalence by hand, I think 77% is still a pretty good result. And in the t-SNE plot, you can still see, similar colors grouping together, but you are getting a bit more mixing going on.
So can you say again what is called the class? What do you call it?
So equivalence classes are if 2 webs exist in the same class, and they are equivalent by the definition, either weak equivalence or strong equivalence.
Mm-hmm.
So all webs of one color will all be equivalent to each other.
And in total, how many classes are there? 16?
So 14 in the full data set.
14.
Yeah.
What are those two classes above it?
As in what's a particular web example?
They are included in the 14, or?
So yeah, sorry, yeah, the 2 classes here are just a subset of the full data set, so they're included in the 14.
Mm-hmm. Okay, thank you.
Thanks.
How did you generate the data set? Did you just pick a web and then you apply SL2Z Hannah-Newton transformations to it to generate equivalences, or how do you generate?
Oh, yeah. Sorry, I think I must have. I was supposed
maybe
to.
You said it. Maybe I missed.
Maybe I didn't actually. So yeah, for generating the data, we first of all just did this general procedure, and then created the full data, and we grouped webs together into their weak equivalence class based on if they had the same invariance. And then for
what I mean is that even with those numbers, you needed to have an algorithm to determine if 2 of them are equivalent, are strongly equivalent, and that's not non-trivial.
For strong, so for strongly equivalent, we created, like I said, the general data to group their weak equivalence classes, and then chose one web from each of the weak equivalent classes, which we know for a fact are inequivalent. And then from those starting webs, we did a random sequence Yeah, sorry, actually, I should have said that. I forgot.
Yeah, no, maybe you said it. Maybe I missed it. Okay, yes, thank you.
Yeah, so thanks.
So you picked exactly 14. You picked 14 elements, all in weak equivalent, in 14 weak equivalent classes, and then out of these 14, you generate 14 classes.
Yeah, exactly.
But then it means that all the brainwaves which are not equivalent, in fact, they are not weak equivalent. Right.
So if the webs are in different strong equivalent classes, they're definitely not weak equivalent. Is that what you mean?
Yeah. So I mean that there are no webs in your data set which are weak equivalent but not strong equivalent.
Yeah, exactly. So like weak equivalence, we say is like a necessary but not sufficient condition for strong equivalence.
Yeah, but what I mean is that in your data set, it's inverted. It's in your data set, I feel like it's equivalence. Weak equivalence and strong equivalence are equivalent, right? Because of how you generate your data set. Is this the case?
So we basically, everything that's strong equivalent is weak equivalent, but when we do our results, so that's sort of the conclusion that we make at the end, is because we're seeing such different results between X and Y, it shows us that actually weak equivalence isn't strong equivalence, that they're different. Because if they were the same, you'd expect you to have similar results here, but they're starkly different.
But how can you have two webs which are weak equivalent but not strong, knowing that the way your dataset is generated is to pick one web from every weak equivalence class and then generate strong equivalent partners for that one? Maybe I'm missing something. Maybe we can discuss later. I don't see how you can have two webs which are weak equivalent but not strong in your dataset.
So we start off with two webs that are weakly inequivalent, and we generate strong equivalent classes. And you're saying you can't have two webs that are weakly equivalent and not strongly equivalent.
Yes.
Yeah, so I think that is true. If they're weakly equivalent, they definitely are strongly equivalent.
So then you don't really distinguish between the hard question is to have two which are weak equivalent but not strong. This would be the hard thing. But it seems that in your dataset you don't have this case.
No, but there are examples of this happening. So I'm not catching where the logic is wrong, but this for sure happened.
So I guess, yes, in your test set, when you test your algorithm, yes, certainly you have that. But in the training set, if you generate it that way, then you don't have it. But okay, maybe it's not too important.
Okay, I mean, I can show you an example on this page. Is we had okay, this is one for 3 legs, this is for 4 legs actually, but so these two webs are weakly equivalent because they share the same invariance, but we couldn't find a sequence of transformations to go from one to the other, so they're not strongly equivalent. Is that an example of what you were thinking?
Yes, that would be an example of what I said, but I said that this thing would not be in your training data set. This cannot appear in your training data set if you generate it in the way you said. And I was just curious about whether this is sufficient to train your network, knowing that you don't have this kind of tricky pairs in your training set. Maybe it doesn't matter.
So I guess maybe because we trained the two investigations like very separately. So we took our weak data, trained it on weak data, tested it on weak data, and we trained for the other case, we trained it on strong data and tested it on strong data. So we really separated the two investigations.
Okay, I see. Thank you.
Ed, what do you have to say?
Oh yeah, I think maybe I could clarify. So yeah, it's just there's these two different data sets. So in this X data set, there's definitely classes that are weak equivalent but not strong equivalent. And the sort of the goal of this was comparing performance on the X data set where we have weak but not strong to performance on the Y data set where they're all strong within the classes.
So how did you create the X data set then?
So it was just general exhaustive search over a space and then compute invariance for all of them. And if they're the same invariance, they're weak equivalent. So there was no actual Hanani-Witten.
Yeah, but how do you know if they are strong equivalent or not?
We don't consider strong equivalence when we're looking at weak equivalence. We really treat them as like separate investigations.
But then we know that if there are two webs that are strong equivalent from the Y data set in the same range, then they must be also weak equivalent. So sure, we know the classes will have some overlap, they'll just be bigger.
Actually, I think I see what you mean. So you're saying in this X investigation, we're going to have examples that are strongly equivalent. So why would it not be? Was that what you were asking? Because we have hard examples in this
I think Antoine is only concerned with the generation of the data, but maybe we can do this afterwards.
Yeah, we can discuss this after. Okay. I don't want to interrupt the whole thing.
Okay, so yeah, the conclusions that we make from all of this is firstly, because we had good results on the X data set, it shows that to some degree, machine learning can learn to compute the invariance and then use that to distinguish weak equivalence. So it's like the first step of determining equivalence. But what's more important, and as we've just been discussing, is the difference between the two different results, so the X and Y results. Because if the two definitions of equivalence were the same and all you needed to distinguish equivalent brainwebs was the invariance, then you would assume that these two results, these two columns would be similar, but in fact, they're very different. So what we conclude was that the invariance are not enough to determine equivalence, and it's a necessary but not sufficient condition. And yeah, as I've already shown, this example here is one particular case where you have two webs that are weakly equivalent but appear to be not strongly equivalent. And finally, so what do we do now? Well, the first thing we could obviously do is extend to more than 3-leg brainwebs, because as Guillermo said at the beginning, 3 legs definitely reduces the complexity of the situation. And as I said, we set out to determine using machine learning whether 2 brainwebs were equivalent or not, but actually the results that we get on our definite definition of equivalence in our Y data are quite poor. So it'd be interesting to look at different algorithms and see if we can improve on this result. But we've really just scratched the surface of all the different things that we could do using machine learning to study brainwebs. So one suggestion from Diego was to potentially use machine learning to look at different phases of the theory. But I'd be interested if anyone here has any ideas of a brainweb type problem that could be amenable to machine learning. And yeah, that's it. I just want to say thank you again to Julius for inviting Guillermo and I to speak. And yeah, we welcome any more questions from anyone. And thank you.
All right, let's thank Elli and Guillermo. Do we have more questions? Okay, if not, maybe let me ask a question that may help with Antoine's question. Can you just say one more time how you generate X and Y?
Yeah, sure. Yeah, I think I probably skipped it.
That would help me because I'm completely lost.
Yeah.
So yeah, basically we generated all possible sets of 9 variables.
You take just every brainweb with some bounds on the numbers?
Yeah,
right?
even
all of them. Mm-hmm.
Yeah, before we get to brainwebs, it's just generate these 9 variables in this range such that you have these 3 conditions. So therefore you get your brainwebs and your brain matrices. And then with that full data set, you then group web matrices together if they share the same invariance. And then you get your weak equivalent classes. And then that was 14 different classes. And then you choose one web from each of those classes, which are weakly inequivalent. So you know that for a fact they're inequivalent. And then you do the sequence of like random transformations like SL2Z, Hanani-Witten, relabeling. And in doing so, you then generate strong equivalent classes. I hope that maybe clears things up.
So yeah, so I will just repeat my same question. But so then in this set that you generated that way, if 2 brains are weak equivalent, then they are strong equivalent.
Yeah.
So you agree that?
Oh, no, wait.
You agree that strong and weak equivalents are equivalent in that generated data set.
If they're strongly equivalent, they're weakly equivalent. But no, what we concluded that is if they're weakly equivalent, they may not be strongly equivalent.
I think
still don't see how you can get
what might help clarify this is that after you generated all the webs, you compute all the invariants for all of them, group them together, you then stop there. That's the X data set that's separated aside. And then to generate the Y data set, you use a few webs, starting webs from the X data set, and then do the moves. So in generating this X set, there's no SL2Z, there's no Hanani-Witten moves, nothing of that.
So to generate the Y, you don't take the X data set and then act with Hanani-Witten.
Not the whole thing, you only just take one web from each.
Yeah, for Y, you just take a sample of webs from each class and do the moves. So the Y is explicitly strongly equivalent because the moves are done, but the X, there's no moves done, so we can't say
now the question is, in Y, how do you know that two webs are for sure not strongly equivalent? Because you've taken two webs which you know are weak equivalent, but you don't know if they are strong equivalent. Then you generated many strong equivalent guys for those two, but you still don't know if those two things are strong equivalent or not.
So we know that two webs in the strong equivalent class are strongly equivalent because we've literally done the transformations, we've done the sequence to get SL2Z Hanani-Witten.
But now I'm talking about two in the same weak equivalence class. For both of them, you generate a strong equivalence class around them.
We
but
only
you still don't know if these classes are the same or not.
Yeah, we only take one web from each weak equivalence class. So we never take two webs from a weak equivalent class.
Okay, but now I'm back to the previous question. I will, maybe if someone else wants to ask a question, I'll go back to this later.
Yeah, maybe you should formulate your question as an algorithm for a machine learning.
Yes.
Okay, Oren.
Well, I guess I think of two interesting questions, but I don't know how amenable they are to machine learning. And one goes back to, I guess, Ami's question about classification. I think the interesting question for classification in this case is to fix I, to fix the rank of the dimension of the Coulomb branch, and ask how many theories there are, with three legs, so with no mass deformations, and a fixed dimension of the Coulomb branch. So instead of fixing the P's and Q's and the N's, somehow fix I. But I guess that it's more complicated to write down an exhaustive list. But that would answer the question of classification. And the second interesting question relates to having more legs. If you have more than three legs, actually the condition for supersymmetry is probably not I greater than or equal to -2. There are examples that satisfy this condition that are not supersymmetric.
Yeah.
So then the question is, can you machine learn whether a given web is supersymmetric or not by showing that it's equivalent to something which is obviously non-supersymmetric?
You mean machine learning the S rule?
Well, machine learning the generalization of the S rule. Whatever that is. Again, so I really have no idea how to formulate it in the language of a machine learning problem, but those are I think two interesting open questions.
Yeah, I mean, I guess the determining whether the satisfied supersymmetry would just be take away this third condition. Oh, wrong one. Yeah, take away the third condition and just do the first two, and then do it as a classification problem and say, do they satisfy what? Obviously, it wouldn't be I is greater than or equal to -2, but does it satisfy this condition? Yes or no? That'd be definitely something we could do.
Yeah, actually, for the S rule, that would be cool since it's really not doable with common methods, it seems.
Yeah, one way of phrasing it, I guess, would be to take a brain web with 4 legs and to ask if it is breakable into two webs with 3 legs. That would be a very nice question, maybe which is machine learnable because the answer is yes or no. And
yeah, binary classification problems seem to work nicely for machine learning, so we tend to start with those. Yeah, thank you. Some interesting ideas.
Do we have?
Yeah, it would be very interesting. I guess you would need maybe more.
Yeah. So to just repeat Oren's point, given a web, is it supersymmetric or not?
Yeah, definitely. So so there do exist like brain webs that people use that aren't supersymmetric.
Sorry, what?
So I was just asking, so people deal with non-supersymmetric brain webs. It's not always like a condition that you, so like the definition of like supersymmetry in the definition of a brain web?
Well, basically you can test for it. So when you, for example, decompose a brain web, then you want to decompose it into supersymmetric subwebs.
Mm-hmm.
And so basically to know whether a configuration will be supersymmetric or not is very important in order to identify the Higgs branch. So this goes here and it goes under the name of S rule, but then I guess we can say something more generic about overall brain webs.
But you possibly need additional data of ending these 5 brains on 7 brains.
Exactly, you need 5 brains and 7 brains. And it's
the data will be larger.
Problem.
Data would be larger, and you could have n PQ brains which end on 1 or more 7 brains, so that's an additional data.
Even here, you can do it actually here. If you take in your figure here, you take n1 to be negative. Take n1 equal -1. So it's not allowed in your set, but let's assume n1 is -1. And then you do a Hannah-Newton move so that in the transform way, this now all the ni are positive. Now this would be an example of a non-supersymmetric web.
Okay.
Mm-hmm.
So one web whose orbit contains a web with one of the ni negative. That would be an example.
Okay, do we have more questions? Maybe we could thank Elli and Guillermo one more time. We'll stop the recording.